You're live.
All right, you're live. All right. Okay. All right. So last time we sort of talked about, we gave a proof of the existence of trisections, and the handle body one we really gave sort of an explicit way of going from a four-dimensional handle body structure to a trisection. And there's a bit of a converse to that I think will sort of be the running goal of understanding today. So let's state this proposition, which is that X admits a handle body decomposition of type. I'm going to introduce some shorthand right here for the first time ever, just to save myself some writing. Okay, so this is meant to say how many handles there are of each type. Great. This happens if and only if X admits a G K1 G minus N K3 trisection. I guess for some G. For some G, and again, G is going to have to be at least bigger than the maximum of K1 and K3. All right. And so we've already seen one direction of this. All right, so the direction we've already seen is if we're given a handle body decomposition, we can come up with a trisection. And the idea is that we pick a Haggard splitting of the boundary of the 0 and the 1 handles. We make the attaching link of our 2 handle primitive to that Haggard splitting. We make the G big enough so it's primitive, and then we have what we want. Because doing Dane surgery on a primitive link in a handle body gives a new handle body, and the trace of this Dane surgery is a 4-dimensional one. All right, so we've seen this direction. And the idea was to make L, which is, say, the boundary of the 2 handles, primitive to the handle body H2 inside of Y1, which is something like this. All right, so let's think about the other direction. And the claim for this direction is that so now we're given the same direction. Now we're given a trisection, and the claim is that the sector Z2 is, we can basically undo what we did. So we can think of it as H2 cross I union G minus N 2 handles. Okay, so it's exactly the backwards direction of what we've already seen. But I want to do this a little bit explicitly, just because I think it's a little bit nice. Okay, and so let's think about it. So now let's think more generally. Let's think about a k-dimensional genus K 4-dimensional 1-handle body. We can think of this thing as a 3-dimensional handle body of genus K cross I, as we've seen. And I want to think of this as a 3-dimensional 0 handle union K 3-dimensional 2 handle or 1 handles, right? And then this whole thing gets crossed with I. And then of course, as we've sort of observed, this is the same as having a 4-dimensional 0 handle union K 4-dimensional 1 handles. All right. But the other way that I want to think of this is, I guess, is I want to increase the complexity of the handle decomposition of our 1-handle body on the one hand. So I want to think of this as a 3-dimensional 0 handle union K plus N 3-dimensional 1 handles. and then union n canceling three-dimensional two handles. And this is all crossed with I. So this. And this is, we want to think of this as our beta handle body. So these are our initial K three-dimensional handles, right? And over here we have the same thing. Oh, I didn't make it quite big enough. Oh, well, I guess we'll just do one. And what we do is we sort of stabilize the handle body by connect summing it with a genus 1 Hayard splitting. Oh, I don't have to do red. Sorry. I'm trying to talk and write at the same time. Going to green. So here we've added on some three-dimensional two handles, and we've added on, I guess, n of them. We've added on n three-dimensional one handles to our k three-dimensional one handles. So this is sort of a new handle decomposition of the handle body. And when we cross this with I, we get sort of a new handle decomposition of our four handle body. Sorry, I'm just saying random. We get a new handle decomposition of our four-dimensional one handle body. That looks like this. And right, so then the idea is that we can think of this piece as a genus G handle body cross I. Have these n four-dimensional two handles with k plus n. Okay. Oh, sorry, this should be, oh yeah, good. G minus, how is that G minus n? 2. That should be G minus K2, which is what we think of as n. Okay, so maybe I'll just try to say one thing about this. I mean, this is not okay. It's not really any more complicated than saying we can take a four-dimensional one-handle body of genus K and think of it as a four-dimensional handle body of genus K plus n. So the Hayard, one of the handle bodies in the boundary cross I. Okay, kind of like we did over on that panel when we were talking about, we used this fact sort of when we were talking about Loudonback Pointeroo, and when we were, and so what in particular what we see is that these extra four-dimensional one handles and extra four-dimensional twos are coming from extra three-dimensional one handles and extra three-dimensional two handles. Okay, I think I've said that there. And any questions? Hopefully this moderate there. But how does this give us what we want? Well, let's just see. Right. Well, if we can think of Z2 as this handle body and its boundary cross I union a bunch of two handles, then that means we can think of Z1 as the 0 and 1 handles, Z2 as these N2 handles, and Z3 as the 3 and 4 handles. Exactly like that. Okay. Maybe we're moving on to part 3. Trisection diagrams. So we'll sort of leave by. Now, okay, what I hope will become apparent at some point today is, I wanted to work through a full example of how to do this in practice. So once we have the notion of trisection diagram, we'll actually be able to see exactly how you go from a trisection to, say, a handle body diagram. We'll see what the time lets us do today. So a GK bar trisection diagram is a quadruple. Sigma alpha 1, alpha 2, alpha 3, such that, okay, so what's going on here? I guess I can just say one thing. I'm deviating from my notes, but I think it's just becoming clear to me that maybe this is the right thing to say, which is that each triple is a Hagar diagram for a connect sum of k sub I copies of S1 cross S2. I'll make that shorter. I think that's right. Okay. In other words, it's just like a Hagar diagram, except now we have 3 sets of curves on our surface, and we have this pairwise condition that that they give us connect sums of S1 cross S2s. So, okay. Anyway, let's look at some examples. So, first examples include the empty trisection diagram. So this would be a 0, 0 trisection diagram. And this, of course, corresponds to the genus 0 trisection of S4. If we move up in genus, then we have a couple of ways of proceeding. So what I need to do is I need to put 3 curves on this surface which have nice properties with respect to each other. Well, maybe the most naive, or the simplest thing I can do is to make the 3 curves all parallel. So in this case, what we see is this would be a one trisection diagram because the genus is 1, and pairwise, each of the curves is giving us the standard Hagar splitting of S1 cross S2. And I claim that this is S1 cross S3, and I also claim that we already know that from something that we learned when we were talking about bridge trisections, which was we had this notion of a reducing curve. Remember, it was a curve in our bridge sphere that bounded disks in the complements of all 3 tangles. And I talked about how those 3 disks are really describing like a 3 sphere. Right? We thought of the triple curve as the unknot in S3 with 3 disk pages, each of which co-bounds a 3 ball. And so it gave us this sort of like open book decomposition of S3. So I claim each meridional curve on this torus is giving rise to a 3 sphere because it bounds in all 3 handle bodies. And so what we're seeing is a circle with 3 spheres. Okay, cool. So some more examples. Well, I guess maybe I'll add this one. Because this was a type of trisection that we've already classified, which is where we have the connected sum of some number of copies of S1 cross S2. So this is the connect sum of G copies of S1 cross S2. We sort of already classified GG trisections, and from this description we can see that this is a trisection diagram for such a thing. All right, more examples. So the genus 1 examples are interesting. So let's keep thinking about them. So maybe in any case, we always have our alpha curve looking like this. And maybe we start off like we did before, thinking we can make them all parallel. But then we decide at the last minute we want to deviate and make green a little bit more interesting. Well, the only thing green can really be is parallel to the red one, and the blue one, which would give us 1 copy of S1 cross S2, or it could be dual to it, which would give us a copy of S3. And so maybe we choose it to be dual this time. And so this is an example of an unbalanced 1, 0, 0 trisection diagram. And this corresponds to S4, as I guess we'll see at some point, but maybe not right now. And then the thing we could do is we could make none of the curves parallel, okay? If any of the curves are parallel, we're either gonna get this or this. So we need all of the curves to be non-parallel. Now, pairwise, if we have two curves on a genus 1 surface, that's describing a Hagar diagram for a lens space, right? In pairs, these curves give Hagar diagrams for lens spaces. And we want them to be all giving lens spaces that are either S1 cross S2, or except in this case, we don't want that because we don't want parallel curve. So we want them to all be S3. So the question is, how many ways are there to put a curve on here so that it will pair with red and blue to give S3? And the answer is that there's exactly 2 ways to do that. We could choose a 1-1 curve, or we could choose 1-1 curve. And the 2 choices correspond to CP2, bar, and CP2, and they're both 1-0 trisections.
How do you tell the difference between those two?
How do I tell the difference? I believe it matches with my conventions that if the green is the orientation conventions that we've so clearly laid out throughout the course, that if green is a 1-1 curve with respect to this red and blue. Or is that your question? Like, why is this the bar and this one not? Or is the question what, like?
Well, one question might be, how do you actually prove those 2 diagrams are not diffeomorphic, orientation preserving diffeomorphic diagrams as a four-tuple of things? Is that the question? How do you prove there's no orientation preserving diffeomorphism?
Well, maybe I'll just foreshadow a little bit. How would we get a handle body picture from these? Well, what we've seen is that we're going to want to think of Z2, which is given by the blue and the green exactly in this picture, as giving us the 2 handles, and the 2 handles arise by choosing curves dual to the 1 handles, and it turns out we want to consider them as surface framed curves pushed into the beta handle body. So, yeah, but okay, but maybe a good exercise would be to check using that toric picture that I gave last time in coordinates. Check that one of these is CP2 and the other is CP2 bar. That should, based on the coordinates, you should be explicit and be able to explicitly see which one is which. Cool. Okay. And then maybe for completeness, I'll draw one more picture. And maybe I'll draw it. Maybe I'll draw it like this. So this, you can check, is a 2-0 diagram. So it's genus 2, and it's pretty easy to see that. So it's genus 2, and it's pretty easy to see that that pairwise the diagrams give standard Hagar diagrams for S3 of genus 2. And it turns out that the 4-manifold described by this trisection is S plus S2. And again, maybe an easy-ish way to see that is that if you do this algorithm, which I hope to someday explain to you, on the gamma curves, you push them off into the beta handle body, and you see a hot link with 0 frame components, which was the diagram that I black boxed as a diagram for S2 cross S2 in the previous picture. So we have an equivalence of black boxes via black box. But we're going to have to be happy with that for now. Okay, and then I guess the corollary that deserves to be stated is that let's say any 4-manifold, any sock, can be described by a trisection diagram. This follows from the existence of trisections because we can just consider the cut systems of curves corresponding to the spine. And moreover, any two trisection diagrams corresponding to diffeomorphic maybe we'll say respectively as a topic, trisections are slide diffeomorphic and then maybe just respectively slide equivalent. Okay. I think I'll just not say anything about the usual caveats of isotopic versus diffeomorphic at this point. Okay, so the thing I wanted to do next was work through an extended example of going from some description, maybe a banded link description of a knotted sphere in pore space to a curvy diagram of its double branch cover, which would pass through a bridge trisection and through a trisection via a branch coupling. So let's see how much of that we can get through in 20 minutes. Hopefully I won't have to rush too much, but maybe we'll try to get through it. Any questions about this business of diagrams? So this is an extended example. And what this example tells us how to do is it tells us how to go from, say, a bridge trisection to a trisection diagram, or let's just say to a trisection, and then from there to a curvy diagram. So there's two important steps that I think are worth illustrating. One is how to take this branch to get a I've already claimed that the branch cover of a bridge trisected surface is a trisected four manifold, and I've already claimed that you can go from a trisection to a handle body decomposition. And so this will show, hopefully, how to do both of these. So let's start with Fox's ribbon tune-up. At least that's what I'm going to call it. So this was an example we previously worked out the bridge trisection for, so I can skip over that part. But if you'll just remember, the starting input was maybe this description of the two-knot, where we have a ribbon disc to one side, and then we have the same ribbon disc to the other side, and that gives us this ribbon two-knot. And so the first step was to convert this to a banded link, and then convert it to a triplane diagram. So that part we've already done, so let's just recall what the output was. So I think, if I remember correctly, when I did this in class, I deviated from my notes and ended up with something that looked a little bit different than what's in the notes. Whatever I'm showing you right now is what was actually in the notes. So this might look a little bit different than what your notes from the class that I have. But claim that this is a triplane diagram for this ribbon knotted sphere. Okay. So step 3 is to standardize, say either T1 or T2. Okay, and you really have a choice here, and standardize. I'm going to put that in scare quotes because there's actually some tricks you can play here. Maybe when we get somewhere with this, we'll see exactly what we need. So maybe I'll just. The first thing we'll do is we'll factor out these 3 twists from the first 2 tangles, which makes them appear in the third tangle. Maybe I'll go ahead and draw this result. This causes red to look pretty good. And I guess one thing that I do want to say is that when I say standardize one of these, I actually really do mean that I only need to standardize one of them. Actually, if one of them is complicated, it won't bother me. So those three twists appear here. This is going to be really fun for you guys to follow along in the notes. Remember, it's here. So anyway, it's fun. All right, but this is not good enough. Maybe I'll explain why. But I'm going to make blue look even nicer than it looks currently. So I'm going to do a half twist here. This is a nice move, this half twist. 1, 2, 3. So this is why the half twist is a nice move, because it lets me sort of move little bridges out from under each other. So it's going to be a small amount of havoc over here, something like that. But we get to something in the end that we're more or less happy with. In fact, I might just, instead of redrawing this guy, I might just extend him down. It's fine, I'm not going to worry about him too much. And then red didn't really get any nicer, but that wasn't the goal. It did sort of change the sign of that little piece there. So blue became very nice. We got our standard wickets. Okay, and then step 4 is to extract a shadow diagram. So when we were talking about bridge splittings and extracting shadow diagrams from bridge splittings, I think I showed you this sort of detailed way of starting at the top and like doing the taffy machine twisting until you get shadows at the bottom. Okay, so you could run that algorithm on this. Although in this example, I think you can kind of just do it in your head, which is the path we're going to take. Okay, so let's put our red and blue curves on here. So we have a nice point of reference. Nice blue shadows, our nice red shadows. Another thing to remember at this point is this trick that you can throw away a shadow of each color. I think I'll go ahead and do that, just to keep the picture a little bit cleaner. So the red guys kind of look like this. And I'm going to throw away the red arc, which would go here, just because I can. All right, now for the green arcs, I'm definitely going to throw one away because the 3 of them are nicer than the 4th. I don't have to draw it. Okay, so the easiest one to see is this green arc right here. Or maybe I'll promote it to an orange arc. Which, see, will that match what I did in the notes? No. Oh well, only do it once. Okay, and so where does he go in this shadow diagram? Well, he just goes behind everything, and he spans 2 base points, and so he looks something like that. So that's the easy part. So now I want, yes, you know, I can change my mind. This one's going to be green. Sorry. Because the other 2 are more complicated, so I'll make one of them orange. Okay, that's that easy guy. Now the one I'm going to make orange is the one that starts here. Okay. And so what does he do? This one you can actually kind of see directly, right? If you just sort of slide him down the pole, he'll just kind of twist around like that. That's what I mean by doing this example in your head, or in my head. So he starts here, and then he jumps over 2, and then he does a twist and turn around that guy. So I claim that is the shadow of that orange guy. And then lastly, I'm going to pursue this one, this green one. So the one I'm throwing out is this guy. I'm not going to consider that asterisk green arc. So what does this other green guy do? Well, let's see if we can imagine. Well, he has to jump over this little orange foot, but then after that, he kind of can wind around everything just like the other. So he has to jump over like this, but then after that, he can wind around. I can say from experience that this is the sort of thing that you get better at with practice. Just like I tell my pre-calculus students with their unit circle. How are we doing? Oh, we're doing really well, actually. Maybe I should slow down. But are we okay so far? Other than obvious note-taking difficulties. Any questions? Is it clear kind of what we're doing, or does it feel like we're wandering in barricade with a candle? Okay, just to recap, we know how to get a triplane diagram. We did this in dimension 3. Or did we? Did I lift I lifted the trefoil, right? Yeah, so we lifted a diagram for the Hagar, shadow diagram for the trefoil, we lifted to the diagram for the lens space. So that's exactly what we're going to do here. So far what we've done is we've extracted the shadow diagram. And then step 5 is to draw it suggestively. Draw suggestively on a sphere. And so what is meant by that is we want to, I guess I could have said that in this example, what we're going to consider is the two-fold branch cover of this guy, which means we're going to treat each of these bridge points as a cone point of order 2 for the 2 sphere. So the suggestive way to draw this 2 sphere is like this. And the idea here is that this is where my cone points live. And to get from this picture to that one, I would sort of puncture my sphere on the bottom and stereographically project it up so that it's flat. So these sort of ovals are meant to be like right here. There's meant to be these ovals between that correspond to the blue curves. Maybe I can make that fairly precise by saying this is what my beta arcs look like in this picture. And I have my red arcs as well. My red arcs look like this. And remember, I threw away a red arc. And so now comes the interesting part, which is the green and orange arcs. This green guy is pretty easy. He just goes behind everything from the second to last point to the fifth to last point, third, fourth to last point. Okay, and now let's do orange. So orange starts here and comes across the front of our sphere. And then it crosses this sort of region here, which means it's now on the back, and on the back it goes to the next region and then comes to the front. Like that. Change the angle. Like that. And then it goes to this vertex. Oh, no, that's not where it's going. It's got to go over this thing again. Sorry. Go to that vertex. Missing a half twist. All right. Now the big green guy starts off here and crosses the. So a good thing to keep track of when you're doing this is to preserve intersection points. Okay. Everything we're doing from this point on is sort of like a local diffeomorphism. So these points should all be corresponding. So we hit red, then we hit blue, we pass to the back side, we go swinging over here, and then we come out, and we go all the way along the front to here, and then we swing all the way along the back to there. So this is the same picture, just drawn suggestively, with the upshot being that we can lift it to the surface. So I guess 6 is lift to a trisection diagram the twofold branch covering of two-fold branch covering of all of the pieces over all of the pieces. So we have a little bit of hole here.